In this lesson, we're going to look at multiple word problems that can be solved by factoring. And one of the first questions I'd like to do is a question we had done way back at the beginning of this unit as an introductory question. Very common question in quadratics. You want to make a rectangular enclosure, you have a certain amount of fencing. What length and width would give you the biggest area? Now back in that lesson, we had used a table of values, we had investigated all the different sizes for areas. It took quite a long time, but now we have abilities that we didn't have then. So it shouldn't take as long to be able to solve this question if we can come up with an equation to model the scenario. So just like we had started at that point, what we need to do is come up with an equation for this scenario, as I just mentioned. But to start, we have to come up with two equations that take a look at both the area and the perimeter of this fence. So we know that area is equal to length times width for a rectangle. And we know that perimeter is equal to 2 lengths plus 2 widths added together, because it's just this length plus this length plus this width plus this width, so the distance all the way around. Now they told us that the perimeter is 100. So I can replace p by 100 because I know that that's what it equals. Now the problem is neither one of these equations is quadratic. We have to somehow make one of the equations quadratic. What happens in math is when you have one equation that's equal to a number that has the exact same letters or variables in it as the other equation, what we normally do is we isolate one of the variables in this equation and substitute it into the other one. So that's what we're going to do. We're going to take this equation right here. We're going to isolate one of the variables, and we're going to substitute it into the area equation. So it doesn't matter which variable we isolate. Let's say we isolate the L. So I'm going to rewrite the equation here. We're going to choose to isolate L. You could have isolated W as well. That means the 2W has to go over to this side. And because the 2W is adding, it becomes a subtraction on this side. And now we have to divide every term by 2. So we're going to end up with 50 minus W equals L. And we're going to substitute that L into that L. So we end up with A is equal to 50 minus W times W. Okay, replacing the L by 50 minus W. Well, what format is this equation in? This is in factored form. This is the best scenario we can hope for. It's not in standard form, it's not in vertex form, it's in factored form. And when we're in factored form, we can easily find the zeros. So let's do that. We're going to temporarily set the equation equal to 0. We're going to split these two up, as I've shown in class. So we have 50 minus W equals 0, and W equals 0. Now that one's easy, it's already done. We've got to isolate the W here. Now, one little trick you can use, if your variable is negative, we want a positive variable. So instead of moving the 50, Let's move the W over to make it positive. And now we've isolated that width. W equals 50. So these are our two zeros. W equals 0 and W equals 50. So that means the parabola that's modeling the area with respect to the width has a 0 at 0 and a 0 at 50. We need to find the maximum area, so we're going to find the vertex of this parabola. We do that by finding the middle, or the axis of symmetry, which is in this case very easy to calculate. It's just 25. And now we're going to substitute that 25 back into the original factored form of the equation, which is 50 minus W times W. Now remember, this is the length. Let me use a different color for that. This is the length of the rectangle. This is the width of the rectangle. Well, what's 50 minus 25? 50 minus 25 is just 25. Our rectangle is actually not a rectangle. It's a square that has a length and a width of 25 by 25. And if we multiply 25 times 25, we get the maximum area of 625. And I believe the units were meters. Let me just go check. Yes, the units are meters. So square meters. So let's just make sure we've answered the question. What length and width would give you the biggest area? Well, 25 and 25 would give us that biggest area. 625 is the maximum area. So if I plug that 625 where the vertex is supposed to go, there's the parabola that models how the area changes with the width. And that is our maximum area at 625. So we didn't need a big table of values. We already had a factored equation when we just substituted the length into the equation for the area right there. And that gives us the solution to that problem. So here was another problem that we had talked about. You manage, and I had told you to put anything you wanted here. I believe we had used pants at the time. This is a revenue question. So you manage a pants store. You usually sell 1,000 pants for $50 each. You notice that if you increase the price by $1 increments, that you sell one less for each increase. What is the maximum revenue? So at the time, I had introduced the idea that revenue is equal to price times the number you're selling. So our original price is $50 each. Our original number sold is 1,000. But each one of those numbers are being modified by the person who's like adjusting the prices to try to maximize the revenue. So it says, you notice that if you increase the price by $1, so if I increase the price by $1 increments, so that means it could increase by $1, it could increase by $2. So I'm going to put an X next to that because X is going to change the 1. If X is equal to 1, 1 times 1 is 1. If X is equal to 2, 2 times 1 is 2. So now I have a way of adjusting that $1 to make it increments. The X will do that for me. Every time I increase the price by $1 increments, I sell one less. So I'm losing one sale. So my 1,000 goes down by 1. And again, that's each time I increase the price by 1. So I have to put an X beside that one as well. Well, this is also a factored equation. Now we're lucky with these two examples that the equations are factored right off the bat. That won't always be the case, and we'll see some examples of that soon. But for the revenue question and for the maximum area question, these equations are already factored. When we had seen this equation originally, we had to come up with a table of values to be able to solve it, but now we don't. Now we're going to set this temporarily equal to 0. Let's find our two zeros. So we're going to split this up. 50 plus 1x equals 0. 1000 minus 1x equals 0. We're going to isolate for x. So the 50 is just going to go over to the other side in this case. So we get x is equal to negative 50. Now in this case, it's another one where we don't often see the x being negative. This is happening because these are word problems, and that happens sometimes in word problems. But we can easily fix that issue by just bringing the x over to the other side. Instead of bringing the 1000 over to the other side, we'll bring the x over to the other side. So these are my two zeros, negative 50 and 1000. I'm going to find my middle. Now because these numbers aren't pretty, we're going to add them together. Let me try that again. Divide by 2. So that gives 950 divided by 2. Let me do that on my calculator to make sure. I'm sure some of you can do it in your head, but I just don't want to make a mistake. So that's 475. So that's my middle x value. So I can already start to sketch my graph. Now it's not going to be very to scale, but let's say this is negative 50 and this is 1000. Right smack dab in the middle of those two is 475. I want to find my height though. I need the vertex to know what my maximum revenue is going to be. So I'm going to substitute that 475 back into the original factored equation. So I'm going back to my revenue now. Instead of making it, I only made it equal to 0 temporarily to find my zeros. Now I'm going back to R to find my actual revenue. So I'm going to substitute 475 into the equation where the x's are. So I've got 50 plus 1 times x, and 1000 minus 1 times x. And where the x's are, I'm going to substitute 475. Now if you remember, this first bracket is the price bracket. This second bracket is the number sold bracket. So we're about to find out what is the best price to sell these at, and what is the best number to sell them, how many of them to sell. And I just realized that my numbers must be a little off because the price of our pants is about to get pretty significant. I hadn't checked this. I should have checked it ahead of time, folks. I'm sorry. But we're going to add 50 to 475, so that's going to become $525 for our pants. And the numbers we're going to sell, we're going to subtract 1000 by 475, which again I should be able to do in my head, but I'm just going to do on my calculator to make sure. And that gives 525 as well. So our maximum revenue is going to be $275,625. So our numbers may not be very realistic. A $525 pair of pants, pretty expensive, but the math is good. So we now have our vertex of $275,625. And let's make sure that we've answered the question. So it says, what is the maximum revenue? And we've just found the maximum revenue. And we could also say what is the price and how many pants we're selling to get to that price. Let's look at another example. This one is more of a physics example. A football is kicked from ground level. Its path is given by the relation h is equal to negative 4.9 t squared plus 22.54 t, where h is the ball's height above the ground in meters and t is the time in seconds. So what I'm going to ask you to do here is find a few things. I'd like you first of all to find the starting height, of the ball. So because this is a real world scenario here, I'm just going to write the equation out. We have some pretty ugly decimal numbers in here, okay? That can happen, and there's nothing wrong with that. We'll just keep working with it as if they were regular numbers, all right? So how do I find the starting height of the ball? Well, when you're reading a word problem like this and the equation is given to you, the first thing I want you to notice are what are the letters that they've given you. They've given you a height, and they've given you a time. Time shows up a couple of times on this side of the equal sign. If I'm looking for the starting height, that means I have to solve for that number. But to solve for that number, I need to sub in a time. Well, what time value am I going to use to find the starting height? Well, what time do stopwatches usually start at? They usually start at 0. So we're going to sub in our time is equal to 0. And I didn't need to do any other math here. That's the only thing I need to do. I didn't have to factor or anything. We'll get to that in a minute. But what happens in this case is my starting height is just going to be 0. So the next thing I could ask is, when is the ball going to hit the ground? Now the word when means find a time value. That means we have to sub in a height. Now what height are we going to sub in to be able to find when the ball hits the ground? Well, what height is the ball when it hits the ground? It's at height equals 0. So we're going to take our equation, we're going to replace h by 0. But here's where we run into a problem. We can't solve an equation in standard form like this. We have to factor it. So what can we factor out of those two things? Now, negative 4.9 does not go evenly into 22.54. Now, you can still factor it, and some textbooks will do that, but you'll end up with a decimal number in your bracket, which is fine. But I'm going to show you an alternative, because I've been telling you that you shouldn't factor things unless they perfectly fit into the other number as a division. So it doesn't work here, but see how there's a t squared and a t right here? So that means there's a common factor of t. So if I take that t out of both terms, I'm dividing it out, I'm going to have a negative 4.9 t left here and a plus 22.54 left over here. And now I can do my zeros. T equals 0, so the ball starts on the ground. Remember, we set the height equal to 0. So what we're finding here is, when is the height equal to 0? Well, the ball starts on the ground at t equals 0. And then if I isolate the variable, and I have a little bit of math to do here, I'm going to set this bracket equal to 0, just like I was doing before. Let's isolate t. Well, the first thing I'm going to do is move the 22.54 over to the other side. And now I have to get rid of the negative 4.9, which is multiplying t. So let's divide by negative 4.9. So what do we get? I'll use my calculator off to the side. And I'm getting 4.6 seconds. So if I sketch my parabola so far, I know that at 0 and at 4.6 seconds, my height is at 0. When does the ball hit the ground? The ball hits the ground at 4.6 seconds. Now, what other question could I ask? What point do we not know yet? we don't know our vertex. Well, what point is that in the trajectory of the ball? Find the maximum height. Which is usually how these questions are set up. So I need to find my maximum height, which means I need the middle value of my time. Well, from my two zeros, 0 and 4.6, I know that the middle value is 2.3 seconds. So let's substitute 2.3 seconds into our factored equation, which is t times negative 4.9t plus 22.54. So our height now is equal to t times negative 4.9t plus 22.54. I'm just going to make sure I copied that down right. And I did. And I'm going to substitute 2.3 here and here. So I'm just going to do this off to the side. And I'm getting 25.9 approximately, and that would be meters. So the max height is 25.9 meters. All right, so even if our numbers are ugly, decimals like this example, because we have two terms, we can still at least common factor. So this goes back to our lesson on common factoring. We common factored to t, we got our two factors, we split them up, made them equal to 0, found our zeros, 0 and 4.6, found our middle, 2.3, substituted our middle back into the factored equation to find our maximum. Let's keep going. So here's another question, physics question. The path of a stunt coming off of a ramp can be modeled by, this would be a stunt car. I forgot the word car there, sorry folks. So the path of a stunt car coming off of a ramp can be modeled by that equation. So you've got a ramp here, you've got a car, terrible car, coming off of the ramp, okay? Where h is the height of the car in meters and d is the horizontal distance it is from the ramp. So we want to find out all of the similar things that we found out before. So what is the starting height of the car? So our starting height, we're looking for an h. That means we have to substitute a distance. Well, the original distance would be 0. The starting distance would be 0. You usually start on 0 on the graph if you have the choice, okay? So that's our starting distance. So that means we're going to replace all of our distances, oops, sorry about that, with 0. And in this case, because we have this 9.8 number at the end that does not have a d, this makes this one a little bit different from the previous example. We're actually going to end up with a number that's not 0 here, which is 9.8 meters. So this is a pretty tall ramp. For question B, we can ask, when does the car hit the ground? Or at what distance, sorry. It's not when in this case because we don't have a time value. So at what distance does the car hit the ground? So if we're looking for a distance, that means we have to sub in a height. Well, what height are you at when we're at the ground? Our height would be 0. So let's rewrite the equation, negative 4.9d squared plus 4.9d plus 9.8. And as you can see, we have a lot of really ugly decimals here. But in this case, the negative 4.9 has a counterpart 4.9 in the middle here. That means I could factor out a 4.9 for those two. Could I also factor out a 4.9 for this one? And the answer is yes. And I'm going to get whole numbers in each one of those. Now I can't factor out a d because there's no d at the very end, but I can take out a negative 4.9 by dividing it out. I'm going to be left with a 1d squared here, a 1d here, and a 2 here. Oh, and I made one little mistake. Easy one to make. If this is a negative 4.9, that means my signs are going to change because I'm factoring out a negative as well as the number. So that means these two are both going to be negative. This is now a trinomial. So we've just recently finished lessons on trinomials. Let's factor this trinomial. So we're going to take the negative 2, put it up at the top of our tree. We're going to take the negative 1, which is the middle number, put it at the end of the tree. Two numbers that multiply to 2 would be 2 and 1, but they have to add to negative 1. That means the 2 has to be negative, and now they actually multiply to the right sign as well. So our trinomial part, the 4.9, the negative 4.9 is just going to tag along. Our trinomial part is going to break up into these two brackets. It's going to be d minus 2 and d plus 1. Now we're looking at how to find the distance that the car hits the ground at. So we need to solve for a distance when the car is on the ground. So what height will we be at when we're on the ground? We'll be at a height of 0, so we're going to temporarily set this equal to 0. We're going to take our two brackets. Once again, the negative 4.9 isn't considered when we're finding our zeros or our roots because there's no way that that can make the equation equal to 0. The only thing that can make the equation equal to 0 are the two brackets. So if I do d minus 2 equals 0 and d plus 1 equals 0, I'm going to isolate for d. And the further one is going to be the one where the distance is where the car hits the ground. So I now know that there's a distance of negative 1, which is probably before the ramp. There's a distance of 2. Oops, if I scale this up properly here, that would be about here, let's say. Okay, so the car is going to hit the ground at that point at a distance of 2 meters away. So this car is going almost straight up and straight down off of that ramp. Okay, now most likely this is the leaving point off of the ramp right here, which is our y-intercept, all right, which we could calculate if we wanted to. But anyway, let's continue. What would be the max height of this car, which I think is C. So the max height is found at the vertex. So we need to find our middle point. So our d middle, which is our axis of symmetry, is 2 plus negative 1 divided by 2, which is 1 divided by 2, which is at 0.5. So now we're going to substitute that 0.5 into our factored form of the equation. So we're going to take the 0 here and go back to an h, because now we're looking for a height. So we're going to put 0.5 into that equation. Some of this I can do without a calculator. So 0.5 minus 2 is negative 1.5. 0.5 plus 1 is 1.5. And if I put all of that into my calculator, I get 11.025, which we're going to round off to 11 meters. So the max height of the car is 11 meters. And that's where I'm going to end the lesson for today. You've now seen quite a few examples of how to solve word problems with quadratics. please practice with some of the homework questions I'm going to assign, and we'll talk to you soon.